Hello and welcome to this edition of the Monday webinar. So let's see if things work. Yes. Yeah, I'll be talking about multiblock data fusion today. My name is Kristian Hovde Liland. I'm an associate professor at NMBU, so that's the Norwegian University of Life Sciences. This term multiblock data fusion, I will try to give a little bit of definition, but yeah, there are many names in the business. So basically it's called data fusion, it's called multiset, it's called multiview, and of course multiblock. The names are used a little bit differently from field to field. They overlap greatly. In some fields you might find that some of these names are more specified than I will use. I will just talk about multiblock in general as anything that has more than 2 blocks connected together, blocks of data. So the Norwegian or Danish expression "kjært barn har mange navn," or in English, "a favorite child has many names." That goes for a lot of methods in chemometrics and statistics. So first a little bit about multiblock data. These data are now inspired by a previous talk I've had in nuclear forensics, so it might look a little bit strange to chemometricians, but yeah, let's just think about these as our typical NIR data or FTIR data or Raman or excitation emission spectra, whatever. But here we have one source of information, that's one of my blocks. This is another source of information, that's my second block. Here we have a third one, and maybe there's even a fourth one here. These are all now measurements regarding the same system in some way. And my main approach here will be looking at things that have the same samples measured with different techniques. I'll come back to a little bit more about that later on different ways of connecting data. Okay, so in this case, we have 3 of these that are matrices of data. So that means that we have our samples in the rows and we have our features or variables in the columns. And then in this case, there's image data. So the samples will now be whole matrices per sample, giving our coordinates, and then, yeah, 1 sheet per sample. If you extend it further, it could, of course, be multispectral or hyperspectral, and then we would get a 4-dimensional cube and so on. So for simplicity, we'll just forget what type of data this is and only think about these as matrices and this multi-way array. And I'll keep now the sample dimension here in color. Also for simplicity, we'll suppose that we can make some kind of image extraction technique that makes our data fall into the same sample times features like this. So yeah, bear with me on that one. It's just an assumption that makes this a bit simpler for now. Okay, so we start by stacking all of these together, and we see now that we have a shared sample mode because everything fits together nicely here. We find the same sample going across all the different data sets or data blocks in our data set. The alternative could be, for instance, to have a shared variable mode. And here, it could be that we have one set of samples up here that are measured on under some condition, and maybe another set of samples measured under a different condition, but they share the same variables or features. And if we have more advanced couplings, this is L-shaped data, where we might have some let's say we have consumer liking data where we have some products and we have some consumer liking and we have some background about consumers. Could be different things that makes this natural to connect. But my basic example through this talk will be this shared sample node, and then we'll look briefly at the other ones later. Yeah, and finally, of course, there might be a target in here. So that would be our response or our reference measurements that are connected to our samples. So typically there will be like spectroscopic data and metadata on the left-hand side, and then something chemical or other target variables over here. Could be both continuous and categorical stuff over here. So before we move on, let's take one step back, because let's say that we have some blocks of data and we want to analyze these. Maybe this is even before we start collecting data, and we want to see how can we connect these different blocks that we have. So the first thing we talk about is the skeleton. So this is the information contained in the modes and how things are compatible. So in this case, we could, for instance, think of sharing the variable mode, and then we would have this type of skeleton, or we could share the sample mode, and then the skeleton would be like this, connecting then the samples in this way. The next step would be to define the topology. This is the connection between the modes, and now we also included the direction. So going now from the skeleton where we had all possible connections, now we make actually a choice. So the direction first, in this case, these are symmetric connections. So that would be our typical unsupervised cases, or they could be with some kind of direction. And this is where we come to supervised learning. So the asymmetric connections here. And there's also a choice of which blocks should be connected to which. So in this case, the green block over at the left-hand side might be some kind of response, something that we want to explain. And the other ones are the input blocks that we want to use for prediction. And the final piece of the puzzle in this is the linking structure. And this defines how exact or how flexible should the linking be here. So typically these input blocks, they will connect to a score block over here, or score vector, set of score vectors, if we are using component-based methods. And that's basically the methods that I know. So we'll be looking at those today. And this linking to these scores could either be a exact one-to-one relation, so that when you make your scores from one of the blocks, they will match exactly, or they could be a flexible linkage. So typically then just correlating with this common block over here, or common score. Or there could be some decomposition also of this score. So we have the contributions that are common across our blocks and the ones that are distinct for each of the blocks. So there are many ways of connecting these together. One thing we also have to keep in mind is how to scale our data. So scaling is an important issue when you have one block, but it becomes more and more important the more blocks that we have. So the easiest way is to just have variable-wise scaling. This is something that we have to be a little bit careful about, because we might actually do some breakage of how things are connected. We could do block-wise scaling to try to match the amount of information. So this is one way of trying to say that my black block here on the left should have the same impact on the analysis as the pink one, for instance. And there are various ways of trying to do this. Or we could do the opposite, try to weight the blocks to make more emphasis on one of the blocks, saying that, okay, I have complete confidence in the green block here, but I'm not quite sure about the blue one. There's too much noise or uncertainty around that one. Let's give more weight to the green one. That's possible in some of the analyses. Yeah, and some of the methods that we're going to look at are so-called invariant to block scaling, meaning that if we multiply the whole block with a constant or a scalar, it won't affect the analysis. And in some of the methods, that's exactly the opposite. If we multiply one of them with a scalar, then we will also change how things are emphasized and how the final solution becomes. Before we, before we look at some of the methods, let's go again one step back and give some more motivation for this. So I've already mentioned that we have a lot of sources of information, but why do we actually use these sources of information? Well, the most obvious would be to try to maximize the information or optimize our predictions. So let's say that we have some expensive reference measurements in yellow here, and we have some relatively cheap spectroscopic measurements in different blocks here. let's say that I have my NIR and my FTIR and my Raman measurements here, maybe some laser-induced breakdown spectroscopy or something more expensive maybe here. And then I want to see how well can I predict my response. So using only NIR, maybe I'm not catching all the facets. If the response covers something that has with complicated, let's say, fatty acids or types of lipids that are not easily distinguishable in NIR, maybe I would get a better result if I added FTIR or Raman. So that's one of the motivations. I might want to quantify variation or contribution. So maybe I say that, okay, I want to combine NIR and FTIR, but which of these contribute the most to actually explaining my response? Or if I'm not in a supervised setting, which of these are actually giving me most information about my samples, without thinking about their response? Maybe I want to evaluate instruments, saying that, okay, I've got this old NIR instrument and I buy a new one. Or I want to buy a new one because newer is always better in some cases. And I want to see, is there actually an improvement? So for instance, some of the techniques will take one block as the basis and then see how much added information can I get from adding a new one. So this could be for just evaluating purchases or techniques. And then more overarching is this estimation of common, local, and distinct variation. So again, with NIR, FTIR, Raman, some of the information that you find across these different sampling techniques might be exactly the same. You might find some basic fat components, for instance, or basic protein components that are more or less the same across all these techniques. So that would be our common components. And then you might find some local components. Maybe FTIR and Raman has something in common that you won't find in NIR. And then you have distinct variation, which is the variation only found in one of these techniques and not in the other ones. And we can try to estimate this with different techniques. And the final step in this one is the interpreting findings, building hypothesis. So if we are pragmatic, we might say that, okay, instead of thinking of these as actually separate blocks, we can just merge them together and do our favorite analysis with like partial least squares or PCA or something that is easily built, Tikhonov regression or ordinary regression for that sake. Maybe we'll get actually better predictions by just merging things together, at least if you keep the scale in mind when we merge these together. However, in a multi-block analysis, we might get better interpretation of the results because we more easily distinguish which part of these block contributions are relevant for the response. We get maybe plotting of each of these, of the results, looking at, let's say, loading weights and scores and the usual culprits. So yeah, interpreting findings is one of the things that we hope that we can do better with multi-block. And as I mentioned, I'm mostly familiar with the component-based modeling, and it has a lot of nice properties. What we hope for is that we find some stable subspaces. So meaning that we find simple linear combinations that span most of the variation in our data with fewer variables or features than the original ones. So typically these are, as I said, linear combinations of original variables where we hope that we can gain some interpretation. If this X here is some spectroscopic data, in this case it's Raman data, we hope that these stable subspaces that we find actually convey some information that is connected to some domain knowledge. So these could, for instance, be connected to the vibrational modes of our molecules. So say that we have some CO stretch or double bonds or something that will actually give us peaks in different positions. And we can use this as part of the validation of our models, because we see that, okay, this first component contains most of this and that. And if we connect this to a response, this makes sense that we would find these separate components when trying to predict, for instance, then a fatty acid profile or something. We also get some insight into our samples, how they relate to each other. So it's easy to look for patterns there too. And we can use this for prediction. And then we would do this component-wise. So looking at one-on-one subspace direction in our data. In this case, going from no components where we only use the mean value of the response, and then adding one-on-one component until we get to something that looks stable, where we hope that there is less noise than if we use the full data set, but still a reproducible and stable subspace direction. So now let's move to one of the methods that I'll be presenting. And the first case is the simplest one that we can see. It's the unsupervised case where we only look at common variation. And this little helping figure up here shows us that we are now looking at the shared sample node, because that's where I am most comfortable. And the first method is the simultaneous component analysis. So this one has proven its worth and has been expanded in a multitude of methods in the last years. And the basic model looks like this in the shared sample mode. So our blocks XM, those would then be our typical NIR, FIR, Raman data, or whatever we are analyzing. Then we have our scores and our loadings. And as you can see now, the scores, they will be common across all the samples. So that's just one T, while our loadings, they will be separate per block. So you see there's one index per block here. So it would either be 1 or 2 here, corresponding to our M. And we will also get errors per block in this case. So we're decomposing this into something that has a common score variation, common sample variation, but separate loading variation. So that's the basic principle here. And we could add constraints to this, because if you just run this and use, for instance, a alternating least squares for estimating this, we will have no guarantees on how the solution will look. But if we add a little bit of constraints, for instance, orthogonality between components, maybe non-negativity or some kind of sparseness, we can force quite a lot of structure into this, and also get reproducible components that convey the information that we hope we will find there. So this is like the basic building block. Now, in this type of analysis, there's a plethora of different methods. Some of them are quite overlapping in how they're built, and some of them have more specialized versions that do different things. So one of them is this multi-group data analysis, which is very related to SCA. We have STATIS, we have multiple factor analysis, generalized canonical analysis, and we have one of these umbrella methods, this regularized generalized canonical correlation analysis, or just RGCCA. Optimal scaling is also available in a multi-block version for this type of problem, and also nonlinear PCA you can find it in this way. Yeah, but for the example, SCA is more than enough. And just as a side note, the original SCA was a variable mode connection. There was, so this is the second edition. Now let's say that you have heterogeneous data instead of just simple spectroscopic data. So what do we mean by heterogeneous? Well, maybe there are different scale types. So we could have nominal data, ordinal, interval, ratio, or absolute scales that could represent different types of data. Let's say that the nominal is categorical data. The ordinal are some survey data. So for instance, assessing some product on a scale. We could have interval data, so calendar time, for instance, ratio scale data, so for instance, the length of something, and maybe some absolute scale data that would be, typically counts of something. And all of these have quite different properties. If you want to do statistics on these, you would have different methods that would be allowed, and different transformations that are allowed to do. So if we disregard that, we could do just implicit handling of these types of data. Just scale all the blocks to whichever scale we feel comfortable about, and then use our ordinary methods. This will work to some extent, but we are losing a lot of this special information or special type that we have in these different scales. So to do this properly, we should do explicit handling of this, and then we would end up with having to look at probability distributions, maybe optimal scaling, or representation matrices, or copulas. So these are different ways of actually using the distributional properties of each of these different scale types, and either compensating for them or leveraging them when you merge your data together and analyze this. SCA, of course, has a method for this. You have generalized SCA and also this exponential family SCA, which explicitly model each of the different exponential families needed here. Next on the list today is unsupervised again, but now we are going to look at common, local, and distinct variation. I already mentioned this concept, but in this case, it's visualized using a set of circles, so a Venn diagram, where we have the distinct variation here in the outer part of the circle. Then the local variation is what is shared between two of these circles. So we have three of those. And in the middle, we have this common part, which is something that's shared between all of these. And this is only conceptual. This is only thinking about the variation contained in this data sets. This is not actual samples or variables that are shared, but they're common information. And we'll again look at the shared sample mode. And the main method for this, I would claim, is DISCO. Distinct and common components. This is an SCA again. So starting with the SCA solution, then we rotate this towards a target matrix. And again, in the sample mode, it is the loadings that we make a target on. Had it been the opposite, if we were in the variable mode, it would be the scores that would be the target. And the target works like this. If we have X's in the target, it means that we don't care too much about what happens here. If we have a 0 in our target, it means that we will try to get a 0 in this position. And this is made up in such a way that we have the first block up here, the second block in the middle, and the third block in the bottom here. And the columns would represent our components, meaning that if we have all X's here, this would be a common component because there is signal everywhere. And if we don't have anything in the middle here, it means it's a local component because it has data from the first and the third one. And in the third component, we only have signal in the second block, meaning that this is a distinct component for the second block, and so on. And this rotation is not an exact thing. We are just rotating towards it. And we have to set up this matrix either completely manually based on our domain knowledge, or we just have to try a lot of different versions of this and rotate towards it and look which gives us the best fit in this target matrices. And the result is that we get now components that have these different properties. We are trying to catch the distinct information, the local information, and also the common information here among the blocks. And practically, this means that we could get the proportion of variation coming from different sources. And we also get our scores and loadings that pertain to the same thing here. When I said that Disco is the main method here, it's of course a matter of choice. There are a lot of different methods that also try to do this. Yeah, we have the penalized ASCA, for instance, if you're into the ASCA methodology, and the penalized ESCA. So that's related to this exponential family again. We have the JIVE method, or jointed individual variation explained. PCA, GCA, which does this in 2 steps, where we have first separate PCAs for the different blocks, and then a GCA to try to find the local, global, and distinct variation. And yeah, more different is the advanced coupled matrix tensor factorization, and also actually multivariate curve resolution could be set up in this multi-block fashion to look for common and distinct variation. Yeah, and as I mentioned, again, originally this was a variable mode method, but has been also extended to sample mode. So over to where I am most familiar, where I do most of my work. That's the supervised part. And we'll start with a concatenated version. And now everything is sample-wise connection. So concatenated means that we are looking at multi-block partial least squares. So what do we do here? Well, we start by scaling our blocks, and the typical scale here is the square root of the number of variables in the block. So JM here means the number of variables per block in this case. So simply scaling them and then putting them together in one larger block like this. And then we perform a PLS regression. So we have our target Y here. We get our scores, and we get our loadings, and we get our loading weights, everything from this first PLS here. And then we can afterwards post-process these to get our blockwise scores, blockwise loadings, blockwise weights, and also the contribution from each of the different blocks to the global model. I present this as if this was the only way to do it. The original one was actually a process where you would not start with a concatenated one, but you would have all the blocks separate in the process, make super scores and super loadings. But the result will be the same if you do this in the correct way. And there are a lot of variations also on this method. If you exchange your basic PLS in the first step here with a sparse PLS, you will also induce sparseness in the multi-block solution. Yeah, you're not guaranteed to get sparseness in each of the blocks, but at least the global solution will be sparse. If you exchange your basic PLS with discriminant analysis or PLSDA, then you could do this for classification also. Or if you exchange these with canonical PLS, you could have a combination of continuous and categorical responses. And you can also have additional responses that are not used for new data, only in the modeling phase, which could make a richer room for your loading weights when you're creating the model. So typical data here, we're looking at some Raman data. I made my blocks here with just splitting a set of spectra into 3 regions. So this would be interesting if you suspect that you might not need the full range of the data, or you want to quantify how much contribution each of these ranges have. And I'm going to try to predict some polyunsaturated fatty acids from this one. And with the multi-block PLS, we get our loading weights, or just weights like this. And they are continuous across all the blocks here because there's a global model that works on the concatenated data. And we also get our scores per block like this, so we can see how the samples relate with regard to each of these sub-blocks that we have in our data. Next on the agenda is a sequential version. So now we are not concatenating anymore. We will use the blocks one on one. Still in the sample connection here. And the basic method here is the SOPLS, or sequential and orthogonalized PLS. And the name tells it all. We are doing now PLS one block at a time, starting with our first block, for instance, an NIR block. We do our PLS regression against the response. We get our scores and loadings pertaining to this. Everything is very simple and easy so far. Next, we have to do is to orthogonalize all the remaining blocks on what we have extracted here. So we use our scores from the first block, and then we orthogonalize the second block on the scores. If you have more blocks after this X2, they will also have to be orthogonalized on this first score. And then we do a new regression between the orthogonalized X2 and our response, deflated response typically. And if we have more blocks, we will repeat the process, alternating between our orthogonalization and PLS regressions. Yeah, and we can then estimate the additional contribution from blocks. Every time we include a new block, we can tell how much do we add to the model, which is very similar to a sequential type 1 analysis of variance. So we can set this up in the same manner. And there are many extensions also to this framework. We could add multi-way blocks, for instance. We could use this together with LDA, or we could add design blocks inside here. That's actually the origin of this, using this one design block and one spectroscopic block. At the time it was called LSPLS, and SOPLS just generalizes this to all cases. Another method that I have been included when we developed is the so-called response-oriented sequential alternation, or ROSA for short. This is very closely related to SOPLS and also to ordinary PLS. In this case, we are setting up a competition between the different blocks. So we can look at this as a generalization of both PLS and SOPLS in a way. And each component is extracted from the block that currently explains the most of Y. This means that if we, for the first block here, try to make scores based on X1, and then we try to make scores based on X2 and also on X3, we would have 3 different candidate scores. And whichever one of these gave the best prediction of our response would be the winner, and that would be kept. So in this case, X2 won the first time, so the first score is a pure X2 score. And then we can project and do everything that we need to also have then loading weights and loadings that pertain to the full set of all blocks that we have. Most of this would be 0. In the loading weights, it would be all 0. In the loadings, we could project it down just to get to see what happens there. But basically, we don't need the other things than only the block that we're looking at here. Okay, so then we've found a winner in the first component. We throw away the other candidates, and we deflate our response based on the winning score. And then we set up a new competition, try to see which block explains the residual response the best. And we just have to make sure that our scores are orthogonal to the previously extracted scores, and then we don't actually have to deflate the X or our blocks here. So we repeat the competition for every component, and we get a series of different winners here. Yeah, so block competition, winner takes all, pure scores here. And since this generalizes PLS, all the PLS tools and extensions are possible. We will do our plots, and we will do our predictions. We will do our cross-validations. All of that is just as we are used And if you plot the explained variance for this type of analysis, we could also include then which block was the winner for each of these, for each of the components. That makes sense. In this case, I have two different PUFA measurements for my samples, so the Raman samples. We have the amount of PUFA with relation to the total sample volume, and the amount of PUFA as a percentage of only the fat part of the sample. And our loading weights, they would now pertain to one and one block at a time. So we see that the first loading weight here is this from the second block, and then comes a loading weight over here, and the second or third one over here, and so on. Yeah, so we get more pure ones over here. There's not this continuous connection that we had in the multi-block PLS. A bonus from this is also that we can look at how did the different candidate scores evolve. So in this case, we look at the residual RMSECV. So for the first component, there was quite a large difference between the different blocks. We see that the highest remaining variation would have been if you used the right-hand side of this spectrum, and the winner was quite much lower. So if you're looking at the scale over here. But as we go through the components, then things become more and more similar. So it's very hard to distinguish when you get out into the like 6, 7, 8 component here. And if you look at the second plot here, instead of now looking at the residual, we're looking at the correlation between the components. And they can often reveal a little bit different patterns than we see with residuals. So two components could be very highly related, but still give a bit different residuals, and the other way around. And if you see that, okay, these were very close, and my domain knowledge tells me that in here, I would expect to have more of a certain compound, I could force the model then to choose a couple of components from this block first, and then let the model choose more freely afterwards. So that's one of the possibilities. Yeah, there are, of course, other methods also available here. For instance, the parallel and orthogonal PLS, where you would also get your global, local, and distinct variation. Yeah, and probably other methods too in this case. Now, my main resource for this talk has been this multi-block book, which is coming in May 2022. So this year, if everything goes as planned. At the time of recording this, there's 1 week approximately before we get the proofs for it. And then, yeah, things will move on quickly before it goes into print. You will already find a placeholder in bookstores around on the internet for this. And the book is Multiblock Data Fusion in Statistics and Machine Learning with applications in the natural and life sciences. Smilde is the main author, and then we have Næs and Kristian Hovde Liland, that is me. It has all the mentioned methods from the talk and many more. You will find comparisons of the methods, relations between them, also some recommendations on which methods to use in which situation. You will find a quite large chapter on basic theory, including 1-block and 2-block situations, and some yeah, little bit of linear algebra and yeah, more basic things. You will find also matrix correlation in one chapter. You will see analysis of design experiments, so ASCA type analysis, and also the more complex topologies that were not mentioned here. And there's a whole chapter devoted to only software. And the main software there is a multi-block R package. And this one is already available on CRAN and on GitHub. So this one you can test already. It contains, I think, more than 20 different multi-block methods in addition to some of these more basic methods. And it has common interfaces for most of the methods. So it's easy to test on one method and just switch method to the other one and continue from there. Yes. And I, of course, have to thank Smilde and Næs for including me in the book project and making the basis for this talk. And I have to thank, of course, also big thanks to our scientific and language proofreaders for making the book significantly better. We got a lot of good feedback from these guys, both with regard to what to put into the chapters and details, and yeah, really making this a much better book. So thank you for your attention, and thank you for watching this. And of course, run to the bookstores when this comes out, and hope to see all of you at a conference in the near future. So bye-bye.